Now we've got to prove that the moment of inertia of a uniform rod whose axis of rotation passes through the center is 1/12 ml². Then we are also meant to prove also that its radius of gyration is 3/6 L². So how do we prove this? The moment of inertia of a uniform rod of which axis of rotation passes through the center is 1/12 ml². So let's go. So if I have a uniform rod, the uniform rod of length L, the length is L, then of mass M. Don't forget the uniform rod, we have the mass of M. So, and it was told that the axis of rotation passes through the center. So anyway, we are considering in moment of inertia, we consider the moment of inertia of every particle in the object, then sum all together. So, but how are we going to do it? We're going to fix a particle here first. So we have, let's fix a particle out of the rod. A particle of length, let's say the length of this particle is the x, a very small length out of the whole rod. Then the gap between the particle and the axis of rotation is x. So don't forget that the mass of the object is m and the length is l. Since the axis of rotation passes through the center, that means the axis will divide the length of the rod into two halves. So the length here is going to be what? L all over 2. And the length here is going to be what? Minus L all over 2 because it's on the negative axis of x. So now how do we proceed in proving this? We all know that the moment of inertia of a unit particle is equal to mr squared. That's the mass times the radius squared. That is the moment of inertia of a unit particle. But considering the rod, how are we going to eventually sum it up? Sum all the particles up. So you only get the moment of inertia for the whole rod. So how do we do that? So then we know that if we have small moment of inertia or small mass and the radius of the mass towards the center, so that will give us integral of the I all equals integral of r squared the n. So that gives us I equals integral of r squared the n. Anyway, so we are going to use this now in relation with this small particle here. So the axis of rotation, the distance between the axis of rotation and the small particle is x. So I becomes integral of x squared the n. Now how can we actually transform the n to the x? So there is a ratio that the small mass all over the big mass equals the small length or thickness of the small particle all over the whole length. So meaning the m is what? M dx all over L. So this, now we have this, we can have the integral to be integral of, anyway, we're going to have a limit that is L all over 2 and minus L all over 2. So of which we have x squared, then n all over L dx. So as these are constant, so we have I equals m all over L, integral of L over 2 minus L over 2, then x squared dx. So then we evaluate the integral. So we have m all over L, that is L cubed all over 3 into L all over 2 and minus L all over 2. So bringing out the 1 over 3 here, we have m all over 3L into L cubed, then L over 2 minus L all over 2. So let's continue here. So from there, I can actually substitute the limit. So that gives us m all over 3L into bracket L all over 2 all cubed minus L all over 2 all cubed. So, and that gives us m all over 3L as we proceed. into L cubed all over 8. Then that gives us also L cubed all over 8. So we go. Now we have M all over 3L into this actually is it's going to give us, because that is going to be positive anyway, because L cube evaluated three places. It's going to give us minus. So the minus times this minus gives us 2L cubed all over 8. So by the time we break it down, we have 1 here, we have 4. So then we have, then L can also go here, we have L squared. So that gives us M all over 3 into brackets L squared all over 4. So ML squared all over 3 times 4, 12. So that still remains to be half, 1/12 of ML squared. So we have actually proved that the moment of inertia of the uniform rod of which axis of rotation passes through the center is 1/12 ml squared. Now, we were also asked to prove that the radius of gyration of this particular rod is √3/6. As we all know that I is also equals to mk squared, where k is what? Radius of gyration. Radius of gyration. So that is defined as the distance from the axis of rotation where all the masses are concentrated. So here we have, so as we know that we have this, now we are meant to prove that the radius of gyration is √3/6L, not L squared. So we're going to have 1/12 ml squared equals mk squared. So this goes with this, and we have 1/12 L squared equals k squared. So by the time we find the square root of both sides, we're going to have L all over √12, which is equals to what? K. So simplifying, we have L all over 2√3 equals K. So rationalizing this, we have L all over 2√3 all times 2√3 all over 2√3. So that gives us 2√3L all over, this gives us 12. Then breaking it down, we have 6. So that means the radius of gyration is truly equals to √3/6L. Thanks for watching. Please subscribe to our YouTube channel. Thank you.